Right. So our next speaker is Perry Hart about colimits in the category of pointed types.
Thank you. All right. So, hi everyone. So I'm Perry. This is work with my advisor Begonia at the University of Minnesota, and I'm going to be talking about characterizing colimits in the category of pointed types. Okay, so often in synthetic homotopy theory, it's useful to actually consider the category of pointed types instead of just the category of types. For us, our motivation originally came from trying to an ongoing project of writing down and formalizing a type theoretic version of the Brown representability theorem. So in this case, we're trying to prove representability in the sense of pointed function types, not just ordinary function types. So one thing that came up is it being useful to figure out what types satisfy the universal property of colimits in this category of pointed types. We already, through hits, sort of standard hits, we have types that correspond to colimits in the category of unpointed types, but we want to see what they look like in many cases for the category of pointed types. So in this talk, I'm going to go over a construction that works when the underlying graph or category, if you want to think of it that way, is something called a strong tree, which I'll get into. And this construction takes place with univalence and the assumption that all pushouts exist. In particular, we're not going to just do the kind of the trivial thing and just postulate a two-hit that would satisfy the property. Okay, so we're calling this notion of graph. We have, it's a pair, a type of vertices, an arbitrary type, a binary family of edges. So gamma 1 of x and y is the type of directed edges from x to y. So now I want to get into defining the structure of strong trees. First thing I want to do is look at this index inductive type of zigzags of chains of adjacent edges in the graph gamma. So we sort of have a starting point where we have a base point J naught in our type of vertices. We have a starting zigzag, which we call nil, and then given a zigzag from J naught to a vertex, and then an edge either going forward or backward, we can use right or left to extend the zigzag to that next vertex. Okay, so continuing on describing this the structure of a strong tree on a graph, let's now assume that the graph we have is connected in the sense that for any vertex, you can get a zigzag from the base point to that vertex.
Sorry about that. That's right. Go ahead.
Okay. Yeah. So just continuing with this kind of toy example, if you go along the edge G2, then that zigzag to that vertex is going to be right of the previous one. And then if you go, you see that if you're going to go backwards, you want less. That's what kind of like, these are the intuitive examples to think of. Okay, so I gave kind of a random example, but more useful examples that of graphs that have the structure of a strong tree include the underlying graph of a pushout on the upper left. On the upper right is the underlying graph of a wedge sum of pointed types. You have the natural numbers in the middle, so a sequential colimit, and then you also can sort of as a slightly more sophisticated graph, you get the integers with the the relation that you did, just 0 is related to 1, 1 related to 2, and then similarly for the negatives. That also has the structure of a strong tree. Okay, a couple of just useful facts that maybe you'd wonder about after defining a structure like this is first, you get a truncatedness property if gamma not the type of vertices is a set and the family of edges is a set. You get that the property of gamma being a strong, the type of gamma being a strong tree is a mere proposition or a property. Also, every strong tree, in the sense I just described, is a tree, which has been defined in the previous HoTT papers as the quotient of the vertices by the edges being contractible. And I'm gonna already a lot of you might be wondering that like the results I'm about to talk about, you probably want to know if they can be extended to all trees, and I'll talk about that at the end. But for now, we're looking at what we can prove with the strong tree structure, and the main result is gonna characterize these colimits in the category of pointed types. So for colimits, let's consider a diagram over a graph, and because we care about what's going on in the category of pointed types, I want to assume that this arbitrary diagram has a base point for each type in the diagram, and that each map in the diagram has a proof of pointedness. Now, we can already, just because we have these ordinary, because we have pushouts, we have the ability to form a higher inductive type that has the universal property of the colimit in the unpointed universe, which we denote as colimit over gamma of F with the canonical cocone maps called iota here. But now to get what we want, to get the property we want in the category of pointed types, I now want to assume that gamma, our graph, has the structure of a strong tree. So once we have the strong tree structure, we can take the family of zigzags, the connectedness condition I mentioned, and using general induction on the indexed type of zigzags, we can get a proof that each of the maps in the cocone into the colimit is pointed, where we're taking the point of the colimit as the inclusion of the base point of the BJ naught base point. Okay, so in addition to having these proofs of pointedness from the connectedness, the strong tree condition, the extra coherence condition on this family of zigzags gives us that the cocone that we form of pointed maps with these proofs of pointedness, that actually is a identity. This expresses identity of pointed functions. So it's truly a cocone now in the category of pointed types. Okay. So here's the main theorem, is that if we're assuming gamma is a strong tree, then the pointed type we just made with colimit having the base point of the J naught inclusion, that actually satisfies the universal property of the colimit in the category of pointed types, in the sense that the post-composition map for every pointed type T is an equivalence. So you have that pointed cocone I just described, you can, given a map from the colimit, a pointed map from colimit to T, you can post-compose to get an element of this limit, which is really just the type of cocones, pointed cocones under F, with the base being the pointed type T. A nice way to an immediate corollary, or pretty much immediate corollary, is that the forgetful functor from the universe of pointed types to the regular universe preserves colimits of diagrams over strong trees. And oh yeah, I should mention, it's not like you can just get this if you just take arbitrary graphs. You do need to do something. You need to make some restriction. You can internally prove the negation of this corollary if you remove any conditions on the graphs. And the counterexample isn't hard, but I won't describe it right now. Okay. Okay, so now sort of to the last thing I really want to mention about this work is extending what we just did to not just strong trees, which, as I said, are trees in the contractible quotient sense, but extending this to get this universal property when the colimit's taken over just any tree, which actually corresponds to the classical result in infinity category theory, where colimits were there, sorry, the kind of the forgetful functor from an undercategory to, you know, the corresponding category preserves and creates colimits over weakly contractible categories, which is the notion of tree I'm mentioning here, of contractible quotient. So how do we do this? This is actually something I didn't even include in my abstract because very recently, I very recently just been trying this out. But it seems like the right thing to do is replace the index inductive type I described of zigzags with an indexed higher inductive type generated by two constructors. You still have a kind of a degenerate zigzag at the base point, and then you actually you take a equivalence for any two vertices and any edge between them. You get an equivalence between the types, the corresponding types of these two vertices. This is kind of an experimental syntax still for index higher inductive types, but I'm using this immediately. I'm using it directly like this because in this form, by a paper by Krauss and von Raumer, we get a commuting square for any I and j connected by an edge. And just with a little bit of work, you can end up then getting the reverse implication of tree to strong tree, and then a logical equivalence. Actually, it should be an equivalent. I think it should be an equivalence, just a general equivalence for any graph gamma. So you could do that. There's a lot that immediately still holds, but I still need to check that the full proof of my main theorem respects the new coherence conditions of this indexed hit instead of just the index inductive type. But if it does, then we will get the result for all trees. Okay. So the last thing is just future work. I still need to do an aggregate of the main results. Still writing this down on paper. And then I mentioned at the start that this all came about motivated by trying to give a type theoretic version of Brown representability. So I'll just say how that relates. The very, very rough statement of Brown representability is that if it's a moderately nice functor, meaning that if it takes pushouts to weak pullbacks in sets and it preserves countable coproducts, then it's actually representable on, and this is where strong trees come in. It's going to be representable on particular sub-universes that are going to consist of iterated colimits over strong trees, because as you might expect, we're going to want the universal property of the colimit in the category of pointed types to hold. So we're going to make sure it does with using strong trees, and then maybe trees if the last thing I just said works. But that's it. Yes, thank you.
So are there any questions?
Hey, so you kind of mentioned you have like this one like particular theorem you're trying to prove using all these results. Do you have a sense of whether this work you've done here is more broadly applicable, or if it can be used for other things?
Well, I guess hopefully it would be useful if you're doing synthetic homotopy theory directly, like in the Brown representability case, on the category of pointed types, in the sense you're directly proving things about pointed function types. Because then I mean, it's very, you know, there's a good chance that if you're doing a result like that, you might at some point want to know what colimits look like. So in this case, you'll have an explicit characterization. They're going to look exactly like the colimits in the unpointed case. So you kind of know that you're dealing with the right spaces in that case. So hopefully, I don't have any particulars, but hopefully it could be broadly useful. Instead of question.
Yeah, so well, you have two definitions of being a strong tree, right? And one of them is equivalent to being a tree. But if you assume that if you assume that your trees are built out of sets, then it actually follows from David's very recent result that these two notions of being a strong tree are equivalent, which means that also your first definition of being a strong tree is equivalent to being a tree.
So that holds what's built out of sets?
Well, I mean, I'm not 100% sure because sometimes you make a mistake when you don't write down your arguments and only have them in your head, but it at least should hold if your original graph, like the gamma 0, gamma 1, is built out of H sets. And maybe it holds somewhat more generally.
Okay.
But I would have to think about that.
That's interesting. Okay, yeah, I mean, that's very nice, yeah.
Yeah, this is a very naive question. What happens with these tree diagrams over U and not U star? Is it?
Well, really the point is that when we're considering diagrams in U star, we're describing when the types that satisfy the universal property of the colimit with respect to pointed types is exactly the same as the type that satisfies the universal property of colimits when you consider that diagram just in the unpointed setting.
Okay.
Yeah, I don't know if that answers.
Yeah, also, I don't know, is there a relation between these colimits of diagrams over trees and polynomial functors or containers?
Nothing that comes to mind. Are you just thinking of the notion of tree, sort of like W type kind of tree?
Yeah, I mean, yes. So whether they
I don't have any, to be honest with you, so the things that, let's take the original definition of strong tree, not the work in progress one. That there are many examples that have the useful graphs that have the structure of a strong tree, but I actually don't, I'm not able to sort of take a big class of W types and show that they have that structure. So I don't have anything, it's concrete for the relationship. Yeah.
Thank you.
Anyone else?
Yeah, I was just wondering if you have an example of where you want to apply the Brown representability theorem, because like the classical situation of representing homology is kind of backwards and not like you can't.
Yeah. Okay, so that's what I mean. So I know what you mean. It's kind of hard to construct non-trivial examples where you apply it. I mean, you can construct examples that aren't trivial but aren't really what you want. What you want is a non-trivial cohomology theories. The only thing I have in mind is that if we know that I think it's still an open, it's a conjecture, maybe even believed to be true that that the homology theory from spectra of HoTT actually will satisfy countable additivity, and from that you can take those and then get by putting them in the codomain of a HOM, you get a cohomology theory that satisfies countable additivity. So you could get them that way, but it's much harder, and I don't even know. You're right. The applicability is going to be questioned. Yes.
Okay, let's thank the speaker again. I don't know.